What if Albert Einstein had never been born? It's a question that sounds like science fiction, but its implications are deeply rooted in the reality we inhabit today. Imagine a world without one of the most transformative minds of the 20th century. How would the trajectory of science, the evolution of technology, and the very course of modern history have been altered? The ripples of his absence would extend far beyond the realm of theoretical physics, touching everything from the GPS that guides our cars to the nuclear anxieties that shaped the Cold War. To truly understand what we would have lost, we must first journey back to the world he was born into. A world teetering on the edge of a profound revolution, whether it knew it or not. Let's picture the scientific landscape at the turn of the 20th century. On the surface, classical physics reigned supreme. The elegant laws laid down by Newton and the comprehensive theory of electromagnetism from James Clerk Maxwell seemed to describe the universe with near-perfect precision. There was a confident, almost triumphant belief that the fundamental work was done. Yet, beneath this placid surface, troubling paradoxes were beginning to emerge. Physicists were grappling with the concept of the luminiferous ether, a hypothetical invisible medium that was thought to fill all of space and allow light waves to travel. But every experiment designed to detect it, most famously the Michelson-Morley experiment, had failed, leaving a gaping hole in their understanding of reality. The puzzles didn't stop there. The work of Hendrik Lorentz and Henri Poincaré had produced equations, the Lorentz transformations, that correctly described electromagnetic phenomena but seemed to imply that time and space were not absolute, a notion that was philosophically jarring. Light itself was a conundrum. Its speed was measured to be constant, regardless of the motion of the source or the observer, a fact that directly contradicted centuries of Newtonian physics. Meanwhile, in the realm of thermodynamics, classical theories failed spectacularly to predict the energy radiated by hot objects, a problem so severe it was dubbed the ultraviolet catastrophe. The stage was set, the questions were hanging in the air, and the pillars of classical physics were beginning to crack. Then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that would ignite a firestorm. This was Einstein's Annus Mirabilis, or Miracle Year. These papers weren't just incremental steps, they were radical, conceptual leaps that addressed the deepest problems in physics head-on. He proposed that light itself was made of discrete packets of energy, or quanta, solving the photoelectric effect. He provided a mathematical explanation for the erratic dance of particles in a fluid, proving the existence of atoms. And most famously, he dismantled the need for the ether and redefined our concepts of space and time with his theory of special relativity, later producing its iconic postscript, EHMCE2. Without his unique ability to synthesize disparate ideas and his courage to embrace their bizarre conclusions, these breakthroughs would have remained disconnected fragments. Their assembly by other minds might have taken decades, leading science and history down a very different path. Relativity. The story of its birth is often simplified, but in truth, special relativity arose from solving deep contradictions between Maxwell's electromagnetism and Newtonian mechanics. By the late 19th century, physics was in a state of quiet crisis. Maxwell's equations described light as a wave with a constant speed, which flew in the face of Newtonian physics. The famous Michelson-Morley experiment, designed to detect Earth's motion through a hypothetical ether that carried light waves, had failed, yielding a baffling null result. The foundations of physics were cracking. In response, brilliant minds across Europe proposed solutions. Mathematicians and physicists like Hendrik Lorentz and Henri Poincaré had already laid important groundwork. Lorentz developed his famous transformations, a set of equations that described how space and time measurements could change to keep the speed of light constant. Poincaré, a true polymath, even postulated a principle of relativity, but their work was seen as a mathematical patch, lacking a unifying physical principle. In a world without Einstein, special relativity could still emerge, but probably later, and in a much less elegant form. It would likely have been a slow, piecemeal consensus built over decades by a committee of scientists. The result would be a functional but clunky theory, lacking the profound philosophical shift Einstein delivered. His genius was to sweep away the old baggage of the ether and start from 2 simple postulates: that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is the same for all observers. From these, the entire structure of special relativity, time dilation, length contraction, and the unity of space-time unfolded with breathtaking logic. But if special relativity was inevitable, the same cannot be said for its successor. General relativity, Einstein's geometric reconceptualization of gravity, was a revolutionary synthesis. After 1905, Einstein was plagued by a new problem. His theory didn't include gravity. For 8 years, he wrestled with the challenge, guided by what he called his happiest thought: a person in freefall doesn't feel their own weight. He realized that gravity and acceleration are fundamentally indistinguishable. This principle of equivalence led him to a radical conclusion. Gravity isn't a force but a feature of space itself. Mass and energy tell space-time how to curve, and that curvature tells mass how to move. Without his insight, the full geometric picture of space-time might have been delayed by decades. The consequence of this delay would be immense. Take GPS technology, which depends on precise relativistic corrections. The satellite's high speeds mean their clocks tick slower than ours, a special relativistic effect. But their distance from Earth's gravity means their clocks also tick faster, a general relativistic effect. Without accounting for both, GPS would accumulate errors of nearly 11 kilometers every single day. In a world without Einstein, this technology could arrive later, or in a less refined form, shifting the timeline of satellite navigation, telecommunications, and many modern conveniences. But the impact goes deeper. Particle accelerators are designed around relativity, and our entire understanding of the cosmos, from the Big Bang to black holes and gravitational waves, is built upon the framework of general relativity. Without Einstein, we would be profoundly blind to the true nature of the universe. Quantum theory. Einstein's early 1905 proposal of light quanta helped push physics toward quantum mechanics, but he also famously disliked some of the philosophical implications of quantum indeterminacy. In a world without him, quantum theory would almost certainly still progress, thanks to Planck, Bohr, Heisenberg, Schrödinger, and others. But the debates about interpretation might take different paths. Einstein's skeptical critiques forced clearer formulations and experiments. Without that pressure, some conceptual questions could remain muddier for longer. Nuclear physics and the atomic bomb. Einstein's letter to President Roosevelt is often cited as pivotal to the Manhattan Project. The scientific discovery of nuclear fission in the 1930s forced many hands, and wartime secrecy and geopolitics made nuclear weapons likely regardless of one scientist's existence. However, the timing and political dynamics could shift. A later or different discovery timeline might postpone the detonation of the first bombs by years, changing diplomatic outcomes and post-war power balances, or it might accelerate under different circumstances. The bottom line, removing Einstein introduces uncertainty, not inevitability. Technology and culture. Einstein's popular stature, the public symbol of the scientific genius, influenced how society perceived science and scientists. Without that cultural icon, public engagement with physics might grow different celebrities, or science might be more obscure for longer. This could affect funding priorities, science education, and public trust. Scientific progress without superheroes. The history of science is rarely dependent on single individuals. Ideas are networked, multiple minds converge on similar problems. Removing Einstein would slow and redirect some paths, but many discoveries would still occur, produced by different teams, scattered across laboratories in Europe, and eventually worldwide. In some cases, alternatives, Lorentz, Hilbert, Klein, or later mathematicians, would fill gaps. In others, new creative breakthroughs might come from unexpected directions. Ethics and alternate outcomes. The social and ethical ripple effects could be profound. If nuclear weapons had been delayed, global geopolitics and the Cold War timeline might change. If relativity's delay impacted space exploration technology, our modern economy and military systems might evolve differently. The philosophical debate about determinism and quantum randomness could take alternative cultural shapes. Let's conclude with a final thought experiment. Imagine asking a leading physicist in 1900 to predict the physics of 2000. At the time, many believed their work was nearly complete. Lord Kelvin had famously noted just two small dark clouds on the horizon of knowledge: the inability to explain the energy from hot objects, the ultraviolet catastrophe, and the baffling failure to detect the ether, the supposed medium for light. Our 1900s physicist might predict grand engineering based on Newton and Maxwell, but they would be utterly blind to the revolutions those two clouds were about to unleash. They could never conceive of a world where time slows down, where gravity bends light and where matter and energy are fundamentally the same. Without Einstein, those clouds would still have burst. The solutions were latent. Figures like Hendrik Lorentz and Henri Poincaré were already crafting the mathematics of special relativity, but they were trying to fit their new equations into the old world of the ether. Einstein's genius was one of radical simplification. He didn't add complexity, he took it away. By postulating that the speed of light is constant for all observers and that the ether simply doesn't exist, he provided the conceptual key. Without him, physicists might have stumbled towards the same conclusions over another decade, bogged down in a more convoluted theory. The convergence would have happened, but it would have lacked the stunning clarity of Einstein's 1905 papers. And what of general relativity, his masterpiece? Here, his absence would be felt even more profoundly. The mathematician David Hilbert was working on similar field equations, so it's plausible a mathematical version of the theory would have emerged. But Einstein's path was paved with physical intuition, his thought experiments about falling elevators and accelerating rockets. He saw gravity not as a force, but as the very geometry of space-time. Would a theory born from pure mathematics have carried the same physical insight, or taken longer to be understood? The map of discovery would be redrawn, the landmark of general relativity might be located in a different territory, discovered by mathematicians, and only later interpreted by physicists. The destination is fixed, but the path we take shapes our entire understanding of the journey. So we return to the question, is it the singular genius or the collective ecosystem that drives science? A world without Einstein suggests a profound symbiosis. The collective provides the soil, the accumulated knowledge, the pressing questions, the frameworks for debate. But the genius is the catalyst, the lens that focuses the diffuse light of the community into a beam that burns through old paradigms. Einstein didn't create his revolution from nothing. He built upon the work of others. But he saw a different horizon. The landscape of discovery would eventually be mapped, but the elegance of that map, the breathtaking directness of the route, and the philosophical depth of the final picture, that is the unique, irreplaceable contribution of the singular mind. The universe would be the same, but our story of it would be a far less beautiful one. Subscribe for more what-if facts and counterfactual journeys through science and history.